All right, let's get started. Are we ready? Are we ready? Yeah! Good, good, good. That's what I like to see, the enthusiasm, right? Yeah. Okay. Are we ready there? Put that away, please. Put your computers away, okay, if you are not using for. And remember, no telephone, turn your telephones off, okay? And I need your attention now for, 75 minutes? Are you getting tired of me coming? Okay. All right. I love coming to this class because this is my favorite class. So unfortunately, I don't teach it this semester, so I'm filling in for him. He's traveling again. He travels a lot, right? Mm-hmm. That's what deans do, right? You're really fortunate to have him. Having a dean to teach you, right, the first semester, I think you should be very happy. He's a great teacher, right?
Yes. Yes.
Yes. Okay, so what are we going to do today? Do we know what we're doing today? Integrals, right? All right. Any question you have from the previous material I can help? Anything? No? How was the exam yesterday?
Good.
Good. Well, yesterday, right? Last night?
Last night.
Okay. All right, so let's start then. So what we're going to do, I know when you did the derivatives, you were able to go back, right? Okay, so you did the integration really by going backward, right? But now we're really going to do the integration, okay? So let's see if we can do that. And we're going to talk about the application to dynamics, okay? I guess later on you will talk about the circuits later on, okay? So here is what we're going to do. We're going to assume that we have an object. Oh, bad. Okay, so, and with respect to its position is x of t. Okay? And we all, only thing we know is the acceleration. You know what acceleration is, right? Okay, so that's what we know here. And from there, I need to find the velocity and the position. Okay? So, and you know the units, let's assume that you have the acceleration in meters per second square, right? And the velocity will be then what? Meters per second. And the position then will be simply meters, right? Okay, so what is the problem? Given, this is what you are given. This is what you're given. And what you need to find is the velocity and the position. Okay? Now, let's do that first, the velocity. You know the relationship between the velocity and the acceleration? One person, go ahead.
The velocity is, acceleration is the derivative of the velocity.
Acceleration is the derivative of the velocity. All right, everybody agree with that? Okay, so we know dvt dt is equal to a of t. Now, the reason I wrote a of t on this side, because this is what is given, right? So really, when I give you the acceleration, I'm really giving you the rate of change of the velocity, right? If I know the rate of change, from there, I want to know what the velocity is, right? That's what I want to find. So how do I do that? Any idea? How do I do that? I want to get rid of the derivative, right? And I want to do its inverse function, right? And what's that called? Integral, right? Antiderivative, that's what you already know. So if I integrate on both sides, I have to do the same operation both sides, right? Okay? You're still playing with the telephone, right? Put that away, please. Okay? All right, and don't talk. All right, so if I integrate both sides, okay, all right, so we have this, right? Now, if you go to the math department, they are not going to like certain thing. If I'm integrating in time, okay? So let's say I integrate from starting from 0 to t, right? And then I'm going to like t over here, right? You need to use some kind of dummy variables, right? You can have the same variable, but we're going to be a little sloppy. We're not going to worry about that, right? But when you go take the calculus course, then I'm going to like, you better put some dummy variable there, lambda or tau or whatever, right? All right? So I'm not going to worry about that. Let's not leave it the same thing, okay? So if I integrate, and you know this is the antiderivative, this is simply going to give me v of t, right? And we evaluate that from 0 to t, right? The limits, right? The limits from 0 to t. Now when you do the integration, you find that and then you evaluate at the limits, right? The upper limit minus the lower limits, right? All right, so on the right hand side you have what? 0 to t at dt. All right, so let's evaluate that. The upper limit is simply going to give you v of t, and that's why they don't like replacing t by t. If you had a lambda there or tau there, you're evaluating that at the upper limit and lower limits, right? All right, so minus the lower limit equal to that. And now we have Vt. So that gives me what Vt is. If I take this on the right hand side, Vt is equal to V0 plus and that gives you the expression for the velocity. So what is it saying? It's saying that velocity at time t is equal to what is your initial velocity, right? And remember, we are starting at time t equal to 0. Your initial time is 0. So velocity at that time, and sometimes people, not sometimes, people call this initial velocity, right? Or the initial condition, all right? So you have to know where you are at time t equal to 0, right? And you add to it the integration. And you already know integration in the area under the curve, right? So whatever is the addition you are doing, area under that is going to be your additional part of that, right? Okay? Now remember one thing important over here, that you are starting at time t equal to 0. You're not going to always start at time t equal to 0. It could be different time. So you should be able to do that. So I'm going to slightly modify this. Say my initial time is not 0, but it is t0. Sometime t0. It could be 0, right? Could be 5, 10, or whatever, right? Right? So if you go now, instead of going from 0 to t, I'm going to go from t0 to t. So on this side also, t0 to t, right? And then on the right, this one will be t0 to t, this one will be t0 to, and what would this be? t0. So what relationship you end up getting is velocity at any time t is equal to velocity, whatever the initial time is. So you get more general expression, right? So wherever you're starting at time t equal to 0, what is the velocity at that time, plus whatever you're adding between t0 to t. Okay? All right? So we will be using this later on. Now, so that is the expression for the velocity, right? Now let's assume, because not only that so I found the velocity, right? Expression for that. Now let's find the expression for the position, x of t. And same relationship is true now, that dx dt, the rate of change of the position, is equal to velocity. Right? Exactly the same thing you're going to do what we did here. Let me repeat that. Now you're going to integrate both sides. Oh. Right? And you need to have limits, right? Okay, so let's say I'm going to put right there t0. It could be 0, could be anything, right? t0 to t. Exactly the same way we did this. Now if you integrate that, you get xt, evaluate from t0 to t, right? And then you get on the right hand side t0 to t et dt. All right, so if I evaluate the limits, you get right? So finally you get what? Your x of t, the position at any time t, is equal to what's your starting position is, plus whatever you're adding, the area under the curve. And that is your x of t. So we're going to use these two expressions. Okay? So we're going to use, first, if we're given the acceleration, we're going to use this to obtain the velocity, and then whatever velocity we have obtained, we'll use over here to integrate one. So you're integrating twice to find the position from the acceleration. Is that clear? Understand that? Let's go ahead now, use an example to find out how we're going to do all this. Okay? Now, first thing we're going to do, we're going to take a simple example. And we're going to assume that you have an acceleration as an expression. Whatever that expression is. It could be polynomial, could be constant, could be a first order term, second order, or whatever, right? So let's go ahead and assume a very simple example that you have a ball you drop. This is my stone or a ball or whatever, right? And I'm dropping it from a height of 1 meter. I think you've done this example before, right? When you did the derivatives, right? Okay, the same example at time t equal to 0, okay? At time t equal to 0, I drop this ball from a height of 1 meter. I want to know what is the velocity as I'm going down, and then what's the position, okay? We can use y of t instead of x of t, it doesn't really matter, right? All right, so what do I do here? First of all, I know what the position is at time, and let's call it y. This is a y direction. I think your notes use y, okay? We know y of 0 is 1 meter, right? That's given to us, right? Because we're dropping from 1 meter high. What else we know? When you are dropping the ball, what's the initial velocity? What's the initial velocity? 0, right? We are at rest. So we know that the velocity at time t equal to 0 is 0. What else we know? We know the acceleration, right? What is it?
Gravity.
Due to gravity, right? Okay, so that is, this is my xg minus 9.81 meters per, you all know that, right? Acceleration due to gravity is minus, in this case, minus 9.81, right? Meters per second square. All right? All right, so now knowing that, let's set up the expression for at any time t, that's what is given to you. That's what you have. And from there, I want to find, let's say first let's find the velocity. Is that clear? So we use this expression here. What we have here, let's set up v at any time t. And we're starting at time t equal to 0 now, right? So we can say equal to v of 0, right? And now we have 0 to t. At is minus 9.81 dt. It's constant, right? Acceleration is constant. Well, you should know how to integrate that. First of all, we know that this is 0, right there. Plus, actually, let's take minus out. So it's minus, right? And this is constant. I'm going to take that out, right? You're integrating simply 1, right? And what's the integration of 1? X. X? How can it be an x? What's the variable here? dt, right? So what will that be? T, right? And that's again what I was talking about earlier. When you really go to math department, they're very particular about that. You're evaluating t at t, right? If I should have put dummy variable here, right? If I would have a dummy variable there, I could have put d lambda here, right? Or tau or whatever you want to call it, and then it'll be a lambda over here, right? Whatever the variable over here, right? And now you say evaluate lambda at time t minus a time, okay? But we are a little bit sloppy here. We engineers are very sloppy in terms of math sometimes, right? So again, I'm reminding you, when you go over there, be careful. Otherwise, they don't like certain things, okay? All right? So what do we have here? So 0 minus 9.81 evaluating at the upper limit, right? Minus evaluating at the lower limit, and that's 0, right? So what does it give me? Minus 9.81 t meters per second. So that's my v of t, right? My v of t is minus 9.81 meters per second. Okay? All right. So now we need to find the position at any time, y of t. Knowing again what is the initial position, which is 1 meter, right? Okay, now we're going to use this. This happens to be variable x. We are putting now, because this was in the x direction, we are in the y direction. Okay? And you will see certain books, they always use x as a position. So it doesn't really matter. You all know that it's in the y direction, right? So let's use y. So in this case, y of t, again we are starting at time t equal to 0, right? So we say y of 0 plus 0 to t. What is this vt? Let me put lambda in there again, just to make sure that you get used to that, putting a dummy variable there, right? V lambda, d lambda, right? Okay, we know what v lambda is. V lambda is minus 9.81. Oh, I forgot T here, by the way. Should 9.81 T. Lambda meter per second, right? It's just a dummy variable, right? So we know this is 1 right there, plus 0 to T minus 9.81 lambda d lambda, right? So let's integrate that now. I'm going to take minus 9.81 outside. That's just a constant. Now we have integration of lambda, right? Anybody know what that is? What's integration of x? You have learned that already, right? X to the power n dx. What's that equal to?
X squared over 2.
I have n there.
X to the n minus 1 over n.
Very good. X to the power n plus 1 divided by n plus 1. Right? Now n in this case is 1, right? It's simply lambda, or you can already say that x is a lambda here. Right? So n is equal to 1, right? So we'll get lambda square divided by 2, right? So we have 1 minus 9.81 lambda square divided by 2, 0 to t. Right? Okay. All right, so what do we have? Y of t then? 1 minus, so I can take the constant out also in divided by 2 here. And what's that equal to? 4.905. Right? All right. So now I'm evaluating simply lambda square, right? Upper limit. So what is there? What's there? T square, right? Minus what? Evaluating at the lower limit, right? 0, 0. Okay, so you get 1 minus 4.905 t square. That is the answer. Make sure you put the units in there. And we have the expression for. Now I remember, you should have done in physics. I didn't really have to do all that, really. You should remember physics, that displacement anytime t, first of all, let's talk about velocity. Velocity at any time t is the initial velocity plus what? Acceleration, right? Isn't that what you did in physics? Well, we have exactly, so anytime t is, this was 0, right? This was minus 9.81 t, and that's exactly what we get here. Right? You also learned in physics the displacement is the initial displacement, right? Plus v of initial velocity time t plus 1/2 a t square. Let's see if it checks out or not. We know the initial displacement is 1, initial velocity is 0, right? Plus 1/2 minus 9.81 t square. And what does come out to be? 1 minus 905 t square. Exactly the same thing I got here. Okay? All right? So that, now, I think when you were doing the derivative, one of the questions was, if I throw the ball from with an initial velocity of 0, 1 meter high, what time will it hit the ground? Tell me the time it will hit the ground. How would I do that? You understand? Yes?
So, y of t equal to 0?
Y of t equal to 0. Very good. Because when it hits the ground, my y is going to be equal to 0. And then I can solve for time. So my y was this. So 1 minus, so y of t is 0, 1 minus 4.905 t square. And I can solve that, right? So what will that be? It says minus 4.905 t square equal to 1. T square is 1 over 4.905. So t is equal to plus and minus. And you know can be negative time, right? So you take the positive value, and if you solve that, it comes out to be 0.452 seconds. And that's what you found earlier. Okay? Are you with me? Any question? It's pretty straightforward, right? All right, let's make it a little different problem. It's a very same kind of problem, but let's change the initial values and see what we get. Now, it says we are going to, and it could be, and I think in the back of the chapter, we are throwing the stone from the top of the building, right? But we can do it from the ground, right? Throw the, with some initial velocity, right? So what I'm doing is I'm at the ground level, and I'm throwing it up. Let's say with the initial velocity of 4.43 meters per second. I think you've done this problem again also already, right? All right, now I want to find the velocity and the position. Okay? So let's write down what we already know. We know y of 0 is what? What is y of 0? 0, right? Because we are throwing from the ground. Now if you were throwing from the building, whatever the height of the building is, that will be the initial position, right? All right, what's the initial velocity? That's already given to you, is this, right? And do we know the acceleration? Again, because of the gravity, right? Minus 9.81 meters per second here, per second square. Now, I really don't need to do anything. I can definitely use what I just talked about here to do that. But let's go through the exercise or doing this, the whole thing, just to learn our integration, okay? All right, so first of all, Vt, you're given this. Let's find Vt is V of 0. Again, my initial time is 0, okay? Initial time is 0. So it's a V0 plus 0 to t. Let me put it a lambda d lambda. Okay, now this is 4.43 plus this is minus 9.81, right? So if I take that out, this is minus 9.81, 0 to t d lambda, or 1 d lambda. Okay, so now we're integrating 1. Okay, so how do we get a 1? What is n value of n? If I have a 1 here, what will be the value of n? N equal to 0, right? Like lambda the power 0. So what should we be getting? N equal to 0. It should be simply giving me lambda, right? Okay, so that is lambda evaluated from 0 to t. And that is going to give me V of t to be equal to 4.43 minus 9.81 t minus 0. Upper limit minus the lower limit, right? T minus 0. So which gives me 4.43 minus 9.81 t meters per second. Well, use again. Now I have the initial velocity to be 4.43, right? If I use that formula, right? You should have gotten 4.43 minus 9.81 t. I got that, right? All right. So again, I hope I'm not boring you. Let's call y here again. Okay. Y of t is equal to y of 0 plus 0 to t v lambda t lambda, right? Okay. So what is the initial position now is 0, right? Plus 0 to t 4.43 minus 9.81 lambda d lambda, right? Okay, all I'm doing is putting v lambda up, all t equal to lambda there, right? Okay, so let's do that. Okay, so let's separate it. So first of all, I'm integrating 1 time d lambda minus 9.81 0 to t lambda d lambda, right? So all I did, I separated them. It's a linear property, so you can separate them and do it right there. So we already know what the integration of constant is, 1 here lambda, right? So it's 4.43 lambda 0 to t minus 9.81 n equal to 1 now, lambda squared divided by 2 0 to t. Okay, so let's evaluate the limits. 4.43 t minus 0, remember it's upper limit minus the lower limits, minus, let's take this 2 out, 4.905 lambda square will give me t square minus 0. Right? So what is my yt? Is 4.43 t minus 4.905 t square meters. And that's the answer. Does it checks out with that? Yt, initial position is 0, right? Initial velocity is 4.43 t, that's what I have. My a is minus 9.81 divided by 2 becomes minus 4.905 t squared. And that's exactly what I got. Okay? So that's simple when you have only one values. Okay? What I'm going to do later on is make it a little more complicated. But before I do that, let's look at what's happening over here. Remember I said that this is going to be the area under the curve. Okay? So let's go ahead and graphically see what's happening. Okay? So let's say you are given, in this case, let me explain this case first before I go and make it a little more general. So in this case, we start from, and we were given the acceleration, right? So this was my a of t. What did we start with? Minus 9.81, right? So it was constant. So this is time t equal to 0, minus 9.81. And now time is, let's say any time t here, or t1 or whatever you want to call it. This is my time. Any time t, right? Okay, and what did we talk about? The area under that is going to be, so my velocity is going to be whatever the initial velocity, in the first part it was 0, right? Right? And so if this is 0 plus the area under that is this area. And you know how to calculate that. Did you really have to do the integration? No. I didn't have to do the integration in this case. Simple case, you don't. That's the beauty of looking at it. See, really what integration is the area under the curve. That is it. Okay? So when you do that, what do we get here? This area under the curve, you know, this time that is, right? So it's minus 9.81 t. That's it. Now if I want to know at 2 seconds, then you have t equal to 2 there, right? So whatever the time duration is, right? And that's your answer. That is your velocity. If you had initial velocity, whatever the initial velocity in our first case was 0, so that's why we got it this. Oh, meters per second. So what are we getting? The velocity is coming out to be, let me plot that. Well, I need more space. Maybe put it over here. Okay, this is time t equal to 0. This is my velocity now. It's 0 at time t equal to 0, right? And that, you know, it's the equation of a straight line. Equation of a straight line, right? With the slope of what? Minus 9.81. And it's going to look like this. Minus 9.81 is the slope. So at time t, if I have the same time, that's going to be my velocity. And t could be anything, 1 second, 2 seconds, 10 seconds, whatever, you know what will be the velocity. Now remember, we found that first problem, it hit the ground at 0.443, something like that. I don't remember. 0.443? So if I want to know what's the velocity at that time, you evaluate that at that time, and you know what velocity is going to hit the ground. Are you with me? All right, now what I want to do is, knowing the velocity, I'm going to do everything graphically. I'm not going to go and integrate. Okay, I didn't have to integrate here, right? Now I want to know what is my, I think first problem we did x of t, which was equal to x of 0, which was 1 meter in this case, plus area under the curve here. And you know what that is? This is just a triangle, right? What's the area under that curve? 1/2 the base times the height, right? So what will that be? 1/2. This is t. Okay, minus 9.81 t, right? Oh, I already have to, right? At this time, what will be minus 9.81, right? So that distance is minus 9.81, right? So what do we get here? 1 minus 4.905. Oh, what did I do here? I did something wrong. Oh, I made a mistake. T times t. 1/2 this times that, right? So this should be t squared meter. Exactly the same answer, right? So you don't have to always use the integration, especially in simple cases when you find the area under the curve, right? Only when you have more complicated cube and things like that, that you really need to worry about integrating or exponential function, okay, logarithmic function or whatever that is, which you can really look at the area under the curve easily, right? Okay, if you have constant values or some constant during the duration, you should be able to do that, right? Okay, so basically in your notes, what you have is saying, okay, my acceleration looks like this, or whatever that is. It could be anywhere going like that. And this is some time I want to know what's the area between time t0 to t1 or t1 to t2. So this is my initial time. This is my final time. All right? So in this case, if this is my acceleration, okay, and that's my time, so my A of t is given, what will be my V of t is whatever I'm starting at time t1. This is my initial time now, right? Whatever the velocity is at t time t equal to t1, right? Plus the area under this curve. Okay? Is that clear? And if you can find easily the area under the curve, you don't have to integrate, right? But if you know the expression and it's more complicated, then you can integrate from t1 to t2 and find what will be the value. This will be the value at time t equal to t2, right? You're finding what is the value at time t equal to t2 is whatever the value here plus area under that. In other words, here is what I'm saying. This is my velocity, and let's say I have, this is the value at t1 already. I'm starting here. Okay? And what I'm doing is I'm adding, this is up to here. So I'm adding this thing. This is my area I'm adding in there, and that's what I'm finding here. So this is going to be from here between T1 and T2, right? Is that what we had? So we found then the difference between that equal to this. So that is going to be your V of T2 minus V of T1, right? Right? So that's going to be V of T2, right? So the difference between that we are adding in here, in other words, you are adding from VT1, adding whatever the area under the curve is to find that. Are you with me? So it's really, if you understand graphically, you can save yourself a lot of time. And you understand what this is. It's nothing more than area under the curve. Okay, if you understand that, it's very easy to solve problems. Okay, same thing with the displacement. You're starting whatever, and now you'll be putting the area under the curve here, and then adding that, right? Okay, so let's see if we can use that now. I'm going to give you a problem where I will not integrate. I'll use this area under the curve concept to solve the whole problem. Okay, so let's see if we can do that. Please stop me if you understand. If you understand this concept, it becomes very easy to solve problems. Okay? All right, so let's see if we can. Now, my acceleration is not constant. It's changing with the time. So let's say I have a expression for AT to be something like this. And I say 2 minus 2. This is 2, 4, and 6 seconds. This is the acceleration given. So in the beginning, remember we had something like that. We save A of t here. And you're also given that you're starting at rest. Okay? All right? So in other words, we know my V of t, V of 0 to be 0, and we also going to assume my x of 0 is 0. Knowing the particles start at rest. Okay, well, that's okay. We can start from 0. It doesn't matter where you start from. Okay, so how do we do this problem? By the way, this is how you should be driving your car. Okay, so, all right? But if you are going on a highway, again, just talk a little bit about that. And you put that on a cruise control, hopefully 65 miles an hour, okay? if you're going at a constant speed, what is the acceleration during that time? 0, right? All right? So that's what, this is the cruise velocity. Okay, so when you get the velocity profile, you will see that my velocity is going to be constant. And in this case, I'm not going 65 miles an hour, maybe whatever that comes out to be, right? And what's the initial, what this mean? Let's put some significance to that. What does this mean? Positive acceleration mean what when you're driving a car?
Going faster.
You're right. And when you're putting your foot on the accelerator, right? Right? Isn't that what we're doing? What are we doing here? You're braking now, right? Negative acceleration, right? So what should be happening? Just to know beforehand, and this is what you're going to get. You're going to start with the 0 velocity, something like this, right? We'll find this expression in a minute. You're starting at 0 velocity, and we know at this time you are going to come to a constant. We're going to go constant velocity from here to here. Didn't we talk about that? Some velocity over here, right? And if you're driving, hopefully we're going to go to 65 miles an hour here, but okay? And now between here and here, I want to come to rest again. Hopefully it should look like this, right? So this is called the cruise velocity over here. Okay, so let's see if we can find that without integrating, and then I will integrate that also, show you what you get, okay? Are you with me? So if I know nothing about the integration, I do not know how to integrate. All I know is integration is the area under the curve. That's it. Okay? How would I do that? So, at time t equal to 2 seconds, I'm starting at, so my v at 2 seconds should be what? V of 0, right? Plus the area under the acceleration from 0 to 2. Right? Isn't that what we said over here? Right? So what is the area under that? 4. So this is starting at 0 plus 4 meters. Is that you are doing meters per second? Whatever the unit, let's say meters per second. So this better be 4. Now from 2 to 4, okay, you are at 4, you're adding what? Nothing, right? Area under that is 0, right? It's 0. So it's going to stay at 4, right? We talk about we are going cruise velocity 65 miles an hour, you're going to stay there, right? All right? So that basically stay constant. Now, at time t equal to 4, between 4 and 6, whatever the velocity at 4 plus the area under the curve here, right? You have 4 plus the area under the curve is what? Minus 2 times 2, 4. 4 minus 4 is 0. So I have found the velocity without integrating, right? Okay, well, let's see if we can do by integration. See if we get that. Okay? Now, if it was more complicated, let's say it was exponentially changing or whatever, or x to the power 3 or whatever, you may need to do exactly the same steps. Okay? All right? So we're taking a simple example and doing that. So let's see if we can go through the step by step. All right? So here is what we have. So v of t is v of t0. I'm going to bring t0 now because my time is not going to be always 0, right? It's going to be changing, right? So this is going to be t0 to t a of lambda d of lambda, right? Isn't that the formula we derived? Okay, so if you look over here, my acceleration is changing, it's staying constant from 0 to 2, right? So my intervals are what? 0 to 2, 2 to 4, right, is constant again, and 4 to 6, and greater than 6. So we have 4 intervals, right? So let's do that in each case, because acceleration, this is changing now. It is not constant. Before it was constant, that's why we didn't have to divide up into intervals, right? Now it's changing, right? So we'll say case 1 or whatever. I can call case 1 or simply a 1. Okay, t between 0 and 2 seconds. Right? What do we know? We know that the velocity at this point, this is my initial time, right? So my t0 is 0 in this case, right? Is 0. And what is my at between that? Is 2 meters per second square. By the way, I should write that down here, at in meters per second square. Right? That's what I know, right? Are you with me? And I'm going to use this information to find the velocity. Okay? Between 0 and 2. Remember, I'm finding the velocity any time between 0 to 2. So Vt between 0 to 2. That's what I'm trying to do. Is my initial velocity, which is 0. Now remember, my t0 is 0 in this case. Now this time t is between 0 and 2. Right? Any time between 0 and 2 seconds. All right? And that is what? 2 d lambda. So when I integrate that, I get plus 2t, right? You integrate, get lambda, evaluate upper limit minus lower limit, you simply get t, right? So this gives me 2t. Now let's check that. Okay, it's saying at time t equal to 0. Oh, it's 0, right? It checks out here. At time t equal to 1 second, I get 2, right? So at 1 second, so basically the slope of that is this one, right? The derivative of this is that, you know that, right? The slope of this must be this, right? So that's my slope, 2, right? So at 1 second is 2. At 2 seconds is 4, right? And that's exactly what I have here. So that becomes my initial condition now for the next step, right? I need v of 2 for the next interval, right? So just go ahead and evaluate that. Like we did have that over there, right? 4. Is that clear? Now we go to the next interval. Case 2, now it's between 2 and 4 seconds, right? 2 and 4 seconds. We know v of 2 is, right? That's my t0 is 2 seconds. V of 2 is what? 4. And we know my acceleration during that time is 0. Right? My acceleration during that time is 0. That's what I need, right? That's to integrate, right? So let's put that in there. So what we get, Vt, now this is between 2 and 4 seconds, right? Okay, so this is going to be my V of 2, right? T0 is 2, right? That's why, and this will be 2 here. That's why I set up there T0, right? Now you're going to start at T0, go up to T. T is anywhere from 2 to 4 seconds. So this, whatever I'm trying to find, is between 2 and 4 seconds. Is that clear? Okay, and that's 0 d lambda. Well, this is going to be 0, it's simply going to be 4 meters per second, because this is 4 and this is 0. And that's what I have over there. Clear? All right? So the next interval is going to be between 4 and 6 seconds. And what do I need? I need my t0 is 4 seconds. V of 4 is 4. And my acceleration is what? What is the acceleration here? Between 4 and 6? Minus 2. Is that clear? Everybody see that? Okay. So let's do that. You go up to 445, right? Right? Okay. So V of t between 4 and 6 seconds is what? V at 4 seconds plus 4 to t minus 2 d lambda. Right? Okay. So this is equal to 4 plus or minus 2 outside. This is lambda 4 to t. Right? All right. So this is going to give me 4 minus 2 t minus 4. And this is going to be so minus 2t. Okay, I can take minus 2 out. T minus, so this is 8, 4 minus 4. So t minus 2. Okay, no, I'm sorry, 6. Right? So this is really minus 4 minus 2t plus 8. Right? Which is minus 2t plus 12. So I'm putting that minus 2t minus 6. Or you can leave it the way it is. It doesn't really matter. I purposely did that to show you something. I wrote in this form to tell you something very important here. And I asked my class, I was teaching the other day, to find me the equation of a straight line which is not starting at 0. In other words, find me the equation of the straight line. How would you do that? Let me ask you this question. I want to find the equation of this line. This is a straight line, right? So I want to know Vt between 4 and 6. How would you do that? By the way, slope of this is minus 2, right? How would you find the equation of this straight line? It's y equal to mx plus b, right? Okay, m is, we know, is minus 2, right? How do you find the y-intercept?
Take a point on the line and then solve for the line.
Okay. Do you really need to do that? Why not? How would you find it? How would you find this point? Huh? Remember the first week of lecture you did? First week of lecture. Can I take advantage of that? Data points, right? There are 2 data points you can use, right? You can use this data point 4 or this data point, right? You're given the velocity at 4 is 4, at 6 is 0. Can I take advantage of velocity being 0 at 6? How can you make it 0? T minus 6 at 6 seconds will make it 0, right? Right? So that's why you have t minus 6. You don't even need to find the y-intercept here. T minus 6 will make it 0, and that's the slope. You understand what I'm saying here? You need to know the slope, right? And instead of using this boundary, this value of data point, I'm using this data point, which I know is 0, right? So it's t minus 6. At time t equal to 6, it's 0. That's it. You don't have to worry about finding the so try to use that, okay? It simplifies things. All right? That's just the extra. Anyway, so that is my v of t between 4 and 6. All right, so let's find now. So what would be the value at 6? 0, right? Now case 4 is for t greater than 6 seconds. Because you think you are done, but you need to find what this is. This may not be always 0. You need to find, in this case it's 0, we know that. Okay? So let's see what we should get. Okay? Again, my v of 6, this is my initial condition, is 0. My acceleration is 0 also, right? My t0, by the way, is 6 seconds, right? Agree? So let's set it up. So my v of t greater than 6 seconds is whatever is 6 seconds plus 6 to t any time greater than 6, right? A of lambda d lambda. And we know it's 0, right? So whatever is a v of 6, which is 0. And now we are done. Are you with me? You understand? All right, let's go one step further and then we are done. Okay? We need to find now the displacement. Right? We know the velocity. So I don't have it. If you don't mind, I am going to erase that and try to plot it here. Area under the curve again. Okay? All right, so let's do that. So this is meters per second. This is my x of t meters, right? This is my x of t. All right, I'm starting at 0 because I gave you that. Whatever you're starting at, right? All right, now I'm doing between 0 and 2. So again, 0 plus the area under the curve. So at 2 seconds, what will be my area? 1/2, 2 times 4, right? And that's 4, right? So at time t equal to 2 seconds, I better be having, let me put it 4 over here. What will happen in between? Any idea? This is the, by the way, you went from constant to straight line. 0 degree to 1 degree, right? And when you integrate again, you're going to get second. So you're going to get a quadratic here, right? So this is a positive slope. It's going to be concave up. Okay? That's what it's going to look like. See, that's where now you don't know exactly what that looks like, right? And I'm going to use the integration to find out the equation of this line. Not line, but equation of this polynomial, right? Right? But this is going to be, I can do this way too. Can you tell me what will be the area at 1 second? I don't have to really still integrate. I can find the value in between. At 1 it will be 1/2, 1 times 2. It's going to be a 1. Right? And any time I can find few points and then I can join it. Then I know what it looked like. But I still don't have the equation, right? To do that, I need to integrate. So let's do that here. So in other words, you should be able to check for simple cases by just looking at the area under the curve and then also integrating. So in the exam, you should never make a mistake. Okay? Because you're not been given, we're not going to ask you very complicated. It'll be something like this. Okay? The value may be changing, or we may have little different expression. Could be trapezoidal, could be whatever that is. Okay? All right? Or I could start at negative and then go positive. Okay? All right? So let's go ahead and find that now. I'm finding case for x of t now. Case 1. Okay? 0 to 2 seconds again. What are the things we know? We know t0 is 0. Right? We know x of 0 is 0. And we know v of t. What is my v of t? We already know v of t expression here. Case 1, I erased that. Case 1, this is what? 2t. Right? If you see your notes, we found during that 0 to 2 second, my v of t came out to be 2t, right? So that is 2t. All right? So let's find why my x of t is x of t0, which is 0, plus 0 to t anytime between 0 and 2 seconds. It's going to be v lambda, which is 2 lambda d lambda. Right? Okay, we know this is 0. All right? So it's 2 lambda squared divided by 2, evaluate from 0 to t. Okay? All right? So 2 cancels out. It's simply going to be t square meters. So the expression for this is t square. Makes sense. If t equal to 2 is 4. T equal to 1, it is 1. If t equal to 1/2, what should I get? 1/4. So that's why concave up, right? It goes with this like, anytime you have positive slope, it's going to be concave up. When you have negative slope, concave down. Okay? In other words, this better be concave down here. And we will look at it. You see that? All right? I can find now any time. Remember, this is only good between 0 and 2 seconds. And I know at 2 seconds what is my 4. And that's what I had here. Okay? So let's now do what will be at 4 by graphically first. What will be the value of the displacement at 4 seconds? Anybody? How do I find graphically? I'm starting at 4. What am I adding? Remember area under the curve? So what I'm adding is this. Right? And what is that? It's 8, right? 4 times 2 is 8. So 8 plus 2, 12, right? That's why I needed. So it's not going to be on scale, okay? Because I don't have too much space here. So it's going to be that. And what should look like a straight line, right? Because this is constant. So again, it's not looking right because I need to put on scale here, right? All right? Okay, so what is the equation of that? I should be able to find it, but let's see if we can do that here. All right? So between 2 and 4 seconds, case 2, okay, my x of t is what? X of 2 seconds plus 2 to t v of lambda. Oh, we'll put that in a minute here. What are the t0 in here is 2. My v of t is what? Is constant. 4, right? So this is 4. So what I'm going to do over here, and by the way, x of 2 is 4. So this is 4, 2 to t, 4 d lambda. Right? So this is going to be 4 plus 4 lambda 2t. Right? So this is going to be 4 plus 4 t minus 2 minus 8. So this is 4t minus 4, 4t minus 1. I think I made a mistake. T minus 1, give me 0 here. That's not right. What did I make a mistake here? So this is at 4, right? Plus my value is 4, right? 4 lambda. So 4 over here. So this is minus 8. 4 minus 8 is minus 4. T minus 1. That's not correct because this is telling me at time t equal to 1, my displacement is 0, right? But I should be getting my 1, what was the value? Oh, I'm sorry, I take it back. This is we're doing between 2 and 4, my fault. So at time t equal to 2, I should be getting 4, which is right? So this expression is between 2 and 4. Okay, at 2 this is 4. At 4, 4 minus 1 is 3. 3 times 4 is 12, and that's what we'd have it. Okay, so that is the expression for this one is 4t minus 1. The next one is 4 to 6, right? So my x of t is equal to what? 12. My v of t is what? We know the equation of this line is minus 2t minus 6. Agree? So let's go ahead and integrate. So x of t is at 4, it is 12. 4 to t minus 2 lambda minus 6 d lambda. Okay? So this comes out to be 12. I'm going to take minus 2 out. Okay, so I have lambda minus 6. So this is 4 to t lambda d lambda minus 6 4 to t 1 d lambda. Everybody see that? All I'm doing is taking the constant out and splitting this up. So this gives me 12 minus 2. This gives me what? Lambda square over 2, right? Which is 2, I take it out, that cancels with this, right? So we have simply lambda square. So this gives me 2 square minus 16, right? Lambda square, evaluate at 4 to t. I'm just going a little faster. T square minus 16, right? Minus 6. So I should be actually dividing by 2. This will be 12. 2 plus 12, right? Minus 2 times minus 6 is 12. And then t minus 4. Okay, so what do we get here? 12 minus t square plus 16 plus 12t minus 48. I hope I'm not making a mistake. Minus t square, right? Plus 12t. And you have 12, 28 minus 20. So if you want to take a minus out, t square minus 12t plus 20. So if I put t equal to 4 there, I should be getting t equal to 4. So that's should be coming out to be equal to 12. So minus 16 minus 48 plus 20. And that is my plus 12, right? Okay, and if I want to find out what value is here, I put in, it should go like this, concave down because of the negative sign. And you can find the value at 6. And according to this, it should come out to be, I think, I don't know where that is. Oh, it should come out to be 16. This value should be 16. All right? We'll see. I won't see you on Friday, but somebody else will.